About 71% of our beautiful planet is covered with water. That's why you see the coolest blue color when you look from space, compared to all the other planets in our solar system. But we're still not sure how exactly we got all that water. And what makes us so special that we ended up the only ones with water on the surface and life? Some say the water has been here ever since our planet formed. Let's jump back to that chaotic period about 4.5 billion years ago, when there were clouds of gas and dust swirling across our solar system. So, somehow, water molecules settled from all that chaos and just stayed there. Land mammals dominate our planet today, but we did originally come from water. So this was the main playground for creating life. Or maybe it wasn't quite like that. Some people believe that a long time ago, our planet didn't really have much water. That implies that all of our oceans formed from the water that came from outer space. Could it be that creatures from other planets sent it because they knew it was the key element for life to form and they needed friends? As far as we know, not quite. It's more like our water randomly came from asteroids and space dust. A Japanese robot brought tiny particles from one asteroid back to Earth, and scientists found something cool. They contained water. The water in these particles was probably created because, while coming from the sun, they were interacting with oxygen in space, and that way, we got water molecules. In the outer parts of the solar system where it's very cold, water forms icy objects, such as comets. As our planet moved around the sun, it collected these dust particles along with the water. Over time, this water fell from the skies and filled what we know today as the oceans. So maybe the water on Earth came from both these space dust particles and icy comets crashing into the surface. It's more probable than the theory that our planet had water even since the beginning because it was way too hot for water to become liquid. I mean, we have the best spot in the solar system for life because we're just the right distance from the sun for liquid water to exist. Any farther than that and it would be too cold and we would end up with ice only. Any closer to the sun would mean we'd have to deal with extremely high temperatures. We've already seen that happen to our neighbor Venus, the hottest planet in the solar system. But even though we had a great position, don't forget there was no atmosphere on Earth at its early stages, so nothing could keep that water in place. When our planet first formed, it was very hot and there was almost no air around it. The surface was like a melted rock. As it cooled down, an atmosphere started to form mostly from gases coming out of volcanoes. And it took about 500 million years for the surface of Earth to cool enough to keep water. So at those early stages, it was probably simply evaporating. If water really came to Earth later, comets and asteroids might have brought it here. Both types of space travelers came to visit once in a while, and both had enough ice to deliver the same amount of water as what Earth's oceans contain. This seems plausible, right? But we still don't know if it was an asteroid or a comet, or whether it was just one or many of them. Also, when exactly did all that happen? One way to tell which one brought us this magnificent gift is to look at the chemical composition of space rocks and compare it to that of Earth. One study showed that water molecules on Earth are very similar to the molecules of rock samples received from ancient asteroid Vesta. Vesta is the second biggest object in the asteroid belt, which is located between Mars and Jupiter. Only Ceres is bigger, and this one falls into the category of dwarf planets anyway. It's the brightest asteroid you can sometimes see even with the unaided eye. But the fact that water molecules are quite similar on Vesta and on Earth doesn't necessarily mean that Vesta was the one that brought water to us. It could be some other similar object that came from space. There are studies that have backed up the theory that asteroids brought water, like the one conducted by the Rosetta spacecraft, the first one that orbited a comet. It was also the first space probe that sent a lander to a comet's surface. Thanks to that, scientists found out that water on comets was heavier than most of the water on Earth. But then again, in 2018, there was a new study involving another comet that contained water with a similar composition as the water on Earth. What makes it different from the previous one? Well, here we're talking about a hyperactive comet. Such comets release more water as they get closer to the sun, compared to regular comets. When one of those regular comets gets close to the Sun, its ice turns directly into a gas, and this gas can later become liquid water on the surface of a planet. But a hyperactive comet loses not only ice from its center, but also icy particles from its atmosphere. These icy particles may be the reason why hyperactive comets have water similar to Earth's. There is water in other places across our solar system too, even though it's different from the water on Earth. It's often hidden under the icy surface of moons, such as Europa and Enceladus. Europa is Jupiter's most famous moon since scientists believe there's a giant ocean hidden beneath its icy surface. This ocean supposedly has about twice as much water as all Earth's oceans combined. And where there's water, there might be life. And who knows what type of organisms we might find there one day when we finally take a trip across our solar system. Scientists discovered this ocean using a spacecraft called Galileo. Galileo orbited Jupiter and detected a magnetic field around Europa, which was a sign there might be a big, salty ocean. The surface of Europa is covered with smooth ice, but it's full of grooves and cracks with strange dark streaks and reddish features. Scientists believe the moon's surface is like that because warm ice rises from deep below. Also, Europa's icy shell squeezes and stretches because of Jupiter's insanely strong gravity. This creates heat inside the moon, which is probably enough to keep the ocean in its liquid form. Then we have Ceres, the only dwarf planet we have in the inner solar system. It's small and difficult to study. But a few years ago, the Hubble telescope found out it was actually more of a watery world than a rocky ball like everyone previously thought. And the story remains the same. The mantle is icy, and then there's a mysterious, slushy ocean underneath. Mars also has its own secret stashes of minerals that only form in water. And just like us, the red planet probably got its water from comets and asteroids that smashed into its surface. And it most likely had a lot of water on its surface, rivers, oceans, and lakes, but billions of years ago. That means Mars may have been a good spot to house life a really long time ago. But over time, the Sun ruthlessly pulled away the red planet's protective atmosphere with the help of its rather unpleasant charged particles called solar wind. As a result, liquid water on the Martian surface either evaporated and mixed with minerals or went underground and turned into ice. And this leftover water is especially interesting because it can tell us if there's still life on Mars. Plus, if we ever move to the red planet, it would be good to have reservoirs of liquid there.
So scientists have this idea that some exoplanets, which are worlds outside our solar system, might be water worlds. They orbit their distant stars, covered by global oceans. Even better, some experts claim that our Earth was once the same, a vast expanse of the ocean, and just a bit, if any, visible dry land. At the moment, water makes up 71% of Earth's surface. Our planet experiences continuous movement of water. First, water evaporates, rising from the ocean surface to the atmosphere. Then rains fill lakes, rivers, and underwater reservoirs. Eventually, all this water ends up in the ocean again. Water also plays an extremely important role in the processes happening below the ground. For instance, water content in magma determines how explosive a volcano can be. Anyway, one of the most burning questions about Earth's water is, where did it all come from? It's very unlikely that our planet was simply born this way. The thing is, water has a way lower condensation temperature than some other substances, like silicates or iron. These materials compose the terrestrial planets in the solar system. In the early history of our planetary system, the region where Earth formed was too hot for the oceans to condense at the same time as our planet appeared. So, there's this idea that water appeared on Earth when melted meteorites hit the surface of our planets. Well, scientists disagree. Researchers analyzed some melted meteorites that have been hanging around in space since the formation of the solar system about 4.5 billion years ago. They discovered that those space rocks had extremely low water content. Even more surprising, they were among the driest extraterrestrial materials ever found and examined. In other words, once they melted, there was essentially no water left. These results were very important, since they helped scientists rule out melted meteorites as the primary source of water on Earth. Plus, we can say that this revelation was kind of eye-opening. Imagine the unlikely conditions that aligned to make our planet habitable. Getting water and developing surface oceans on a planet so small and so close to the Sun is a great challenge. If Earth had formed just a tiny bit closer to the Sun, our planet would have been much hotter, and all the water would have most likely evaporated. If it had been farther away from our star, Earth would have turned out to be much colder, and the water would have probably frozen into ice. The team of scientists managed to analyze 7 melted meteorites that had crashed into Earth. Those must have splintered from at least 5 space objects known as planetesimals that later collided to form the planets in our solar system. These planetesimals took part in something known as melting. They got heated up as a result of the decay of radioactive elements in the early solar system. This caused them to separate into layers with a core, mantle, and crust. Plus, the heating and melting of planetesimals apparently led to near total water loss, regardless of how much water they started with. As for meteorites, some of the samples arrive from the inner solar system where our planet is located. The conditions here are relatively warm and dry, so it's no wonder the meteorite samples didn't contain much water. But a few samples were from the colder outer reaches of the solar system. That's from where the water is believed to have come to our planet. But if this water hadn't been delivered by meteorites, what kinds of objects could have carried it all the way across our planetary system? There's one more theory, though, that hydrogen inside our planet played an important role in the formation of the oceans. At the same time, these two ideas are not mutually exclusive. Water could have been delivered to Earth by impacts from some space bodies, like asteroids from the outer edges of the asteroid belt, spanning between the orbits of Mars and Jupiter. And some amount could also appear inside our planet. There's also a theory that claims that Earth gradually grew by accumulating icy planetesimals about 4.5 billion years ago. At that time, it was still only 60 to 90% of its current size. According to this theory, Earth managed to retain a certain amount of water in some form throughout the process of accumulating its mass, and as a result of large impact events. It sounds quite plausible. The examination of the chemical composition of lunar samples brought to Earth by the Apollo 15 and 17 missions indicated that water had already been present on our planet before the Moon was formed. So far, all these ideas remain just theories. At the moment, we don't know for sure how water appeared on Earth. What we do know is that there are many other space bodies that have water in this or that state on their surface, or under it. Let's start with our dear Moon. On Earth's natural satellite, water can be found all over the surface, but it's probably not the water you imagine. You won't find pools of liquid water there. On the Moon, it's mostly ice. Some places have more water than others. For example, the poles of the Moon are regions that never get any sunlight. That's why they're extremely cold, and there's a lot of ice there. Plus, the ice in these areas is often mixed with the lunar soil and hidden deep below the surface. Then there's Jupiter's moon Europa. Astronomers consider this world to be one of the most promising places in the solar system to search for new life forms, all because this moon has a huge saltwater ocean with a depth of 40 to 100 miles. Yes, it is hidden under a layer of ice that is estimated to be from 10 to 20 miles thick. But it is still potentially habitable. Astronomers claim that plumes of water erupt from cracks in the ice shell and release the contents of the moon's ocean into space. Of course, the temperature, pressure, and chemistry are far different on Europa. Scientists don't know yet how the ice behaves there. That's why they can't understand how deep or large the water reservoirs on Europa are, or how long they need to refreeze. Enceladus is the 6th largest moon of Saturn. It's not really large, only 314 miles across. This makes the space body small enough to fit inside Arizona. Wait, we should try that. Never mind. When the Cassini space probe first arrived at Saturn, Astronomers thought that Enceladus was going to be a frozen ball of ice. But then they saw plumes of icy particles and water vapor erupting from geysers on the moon's surface. It became clear that there was a massive ocean between the moon's rocky core and its icy shell. If you've been imagining Mars as an extremely dry place, you need to listen to this. Scientists think there could have been a lot of water on Mars in the past. What makes them think so? They found lots of ancient river valley networks and lake beds on the surface of the red planet. Plus, on Mars, there are minerals and rocks that can only form in liquid water. Mars might even have experienced terrible floods 3.5 billion years ago. These days, there's still some water on the red planet. It's true that Mars's atmosphere is too thin for this water to stay in its liquid form on the surface of the planet. But under the surface, it's a different matter. You can find water in Mars's polar regions, but the only place where this water is visible is at the North Polar Ice Cap. Sometimes salty water flows down crater walls and hillsides, and there are tiny quantities of water in the planet's atmosphere, but it only exists as vapor. Since we know for sure there is liquid water on Mars, could we possibly use this water during the human-operated mission to the red planet? If we manage to do it, spaceships coming from Earth wouldn't have to bring their own water. It would make the cargo way lighter, which, in turn, would decrease the cost of the mission. We would just need to take enough water to get to the red planet and bring along the equipment needed for filtering Martian water to make it drinkable. Well, it sounds simple enough.
When we look at our planet from space, one color dominates. That's why Earth is called the blue planet. About 3/4 of our world is covered with water. But there's a catch. 96.5% of this water is trapped in the oceans. And if you remember the first time your parents took you to the seaside, drinking that water is a big no-no. So, why is ocean water salty and undrinkable? There are two main reasons. The first is runoff water from the land. Rainwater is slightly acidic. Its pH factor is somewhere between 5 and 5.5. For comparison, pure water has a pH factor of 7, and the acid we find in batteries is a bit more than 0. Such rain erodes rocks when it falls on the ground. This releases ions, such as sodium and chloride. They end up in rivers and streams that eventually empty into the ocean. Living organisms remove some of the good ions, but the rest remains. Over time, this increases their concentration in the water. Oceans have their own salt powerhouse. Vents in the sea floor let out a hydrothermal fluid. Sounds complicated, but it's easy to understand. Water seeps down the gaps on the ocean floor. Then, the magma from the Earth's core heats up the water. There is a chemical reaction that frees seawater from oxygen. It picks up metals, such as iron and zinc. The vents on the sea floor release this metallic water back into the ocean. During an underwater volcanic eruption, the process speeds up. Salt and other minerals are directly released into Earth's oceans. Over time, salt accumulates on the seafloor and forms domes. These deposits occur under dry land as well. Some places on the globe have a large number of salt domes. The Gulf of Mexico is just one example. Beneath the waves, they affect the salinity of water. Other factors that determine how salty a body of water is include evaporation, air temperature, and precipitation. The general rule is that salinity is low near the equator and at the poles. All the oceans and seas in between are likely to have high salinity. Scientists estimate that dissolved salts make up 3.5% of the weight of the world's seawater. The waters that empty into the ocean, such as lakes and rivers, are fresh water. So, why is the seawater salty? To answer this question, we must travel into our planet's past. Researchers believe that primeval seas weren't as salty as they are today. But over time, rainfall washed away the rocks on land, transporting vast amounts of salt into the oceans. The process has been going on for more than 3.8 billion years. Today, some 4 billion tons of dissolved salts end up in Earth's oceans every year. The input and output of salt are fairly balanced. This means that seawater's salinity is stable. So, why can't we drink seawater? We already take salt into our bodies with food and drinks. It is called dietary salt. The World Health Organization recommends that humans consume no more than a teaspoon per person, per day. You shouldn't go over that amount if you want to keep your heart healthy. Centuries ago, salted beef and pork were the standard diet of seafarers. Meat was preserved using salt. At sea, fresh fruit and vegetables would go bad after just a couple of weeks. Before refrigeration, this was the only way to keep food fresh. Pickling was another option for storing food. The reason why we can't drink seawater is the salt content. The percentage of this mineral in our blood is nearly 4 times lower than the percentage of salt in seawater. Our body simply cannot process such a high amount of the substance. When we intake salt as part of our diet, we also drink liquids. When you serve pretzels, you probably have a glass of water or juice nearby. It helps quench the thirst and keep the salt levels in check. If we drink water straight from the ocean, the exact opposite happens. We just become thirstier. Our body absorbs both water and salt. They end up in our bloodstream. The organs responsible for getting all this salt out of our blood are the kidneys. But they need water to perform their duty. The higher the salt content, the more water they need to wash it away. When the process repeats itself several times over, you become dehydrated. This is the process of losing water from the body. And there's another catch. You start releasing more water than you take in when you drink seawater. The difference leaves you thirstier than you were when you started drinking seawater. Not a good idea to begin with. But some marine mammals, such as whales, seals, and even seagulls, can drink water from the sea, just like we drink tap water. The kidneys of these mammals are super efficient. Birds have special glands in their beaks that prevent salt from getting inside their bloodstream. Scientists found that the only land animal that can drink seawater is the camel. And if you ever wondered if fish drank seawater, they do. The gills and kidneys help them pump out the excess salt. For humans to drink ocean water, it first needs to go through desalination. This is the process of removing salt from seawater, and there's a lot of it to take away. Estimates show that if we laid out all the sea salt across Earth's landmass, it would be higher than the Statue of Liberty. That's why desalination on a global scale isn't realistic. Right now, less than 0.5% of the drinking water we produce comes from seawater. And the demand for potable water is only going to increase. The current rate of consumption means that the demand for fresh water doubles every 20 years. The biggest issue with desalination is the energy cost. It takes 10 times more energy than other water production methods, and the carbon footprint is huge. Large desalination plants often need to have their own power stations. This is all because of the technology behind the process. Salt dissolves easily in water. It creates a strong chemical bond with water that is hard to break. Desalination facilities mostly use reverse osmosis to achieve this. Large pumps exert pressure on seawater to push it through a filter. Its membrane is so fine that each pore is a fraction of the size of a human hair. The filter allows for water molecules to pass. Larger salt molecules remain trapped in the membrane. For every quarter of a gallon of fresh water the plant generates through desalination, there is the same amount of water that is now twice as salty. Hardly the ideal method of water purification. The idea that humans could drink seawater isn't new. In the mid-4th century BCE, the famous Greek philosopher Aristotle considered using a series of filters to remove salt from water. Ships in the 16th century had small, portable distilleries that could boil seawater. This was merely patchwork, since exposing seawater to high temperatures doesn't make it drinkable. Such thermal processing only sterilizes the water. You would need to catch the steam that evaporates and wait for it to cool down before it's safe to drink. This is a complex and time-consuming method that is probably not worth the effort. Let us imagine for a second that we got rid of all the salt from the Earth's oceans. We would get an endless supply of drinking water. But at what cost? There are millions of animal and plant species that are adapted to salt water. These include plankton, the basis of all marine life. They wouldn't have enough time to adapt to the new conditions. Not all fish are like the salmon, which thrives both in fresh and salt water. The sudden switch would also have a profound effect on our planet. Since freshwater is less dense, it would immediately cause the ice cap in the Arctic to sink by 4 inches. This would trigger the largest tidal wave the planet has ever seen. Although the idea of desalination on a global scale sounds good on paper, we should take it with a grain